So, welcome to the last session. Today I will speak about in general the circuits in car, and so the circuits in the car is a big wide spread of, it contains a wide spread of circuits, and I will focus only in a particular section of it. So I will start with an introduction to give you more or less the idea of what does it mean, the circuit in car, and what is the evolution over the years. And then I will particularly focus on the process which is needed to build a circuit in a car and why it takes a particular attention to it. And then I will, as I said, I will go into the detail in some example, in particular how a radar is done and how the system radar is built together with microcontrollers and the power supply modules. And then I will conclude my speech. So about myself, quickly, so I'm married with one kid, and I like a lot to do outdoor sport when I don't work, when I don't have to take care of the kid. About my education, I did education in Italy, in Padovan, and I got a master's degree in 2012 and a PhD in 2016 in phased array system, RF circuit design. And then about my work experience, I started in 2016 as a RF designer, and then since 2022 I am a manager of a digital RF team with 12 people and some students and PhD students that are working on innovation topics. So to introduce my speech, so I want to focus on the fact that in the last 20 to 30 years, the automotive industry had really an exponential growth of the usage of electronics. So at the beginning, there were only a few transistors in a car, mainly was mechanical driven application, and with the growth of electronics and the integrated circuits, it gets really exponential. And now every piece of car contains some integrated circuits. We can count up to 10,000 of devices into the modern car. And the growth is not stopping, so it will continue with the electrification and with the autonomous driving, as I said, and the connectivity between the car. So as I explained in the introduction, it is very important to understand that in the car, you are dealing with safety. So if your circuit is having some issue, you can create severe problems to the people. You can have some people die, some severe accident. And this means that all the process need to be very well controlled from the material selection. That is where is the responsibility to understand which transistor you want to create, and the reliability of this transistor, to the circuit design step itself, and then going into the direction of the packaging, with the production, the packaging, which is the first interface with the external world. Then, of course, we need to test our circuit. We need to make sure that our circuit are really working in the real environment and with the real condition. This is a very important step that usually in the students' world is under-evaluated, but it's really crucial in the industry. And then, of course, the last piece is the application. So when we have a system with a circuit inside, at the end, this system needs to be used in the application, and there where also the software need to play the role. In the sub-branch of the circuit development, we can further split the circuit development into several steps. We start with a very crucial step, which is often underestimated, which is the requirement definition. And when you will start to work in a company, you will see that you will spend a lot of time in the requirement definition, much more time than in the circuits. And that's why I want to tell you this, because in the automotive circuit and circuit for car is even more important this, because there are not only the requirement related to the performance of your circuit, but you have also the requirement related to the functional and safety of your circuit. This means that your circuit need to need to guarantee a functionality and need to be safe. And going deeper into this understanding, you need to have some way to detect if your circuit is really working or if your circuit is gonna fail. And that's why it is this phase of defining the requirement is really important. Then from this requirement definition, we have the concept engineers that convert the requirement into the parameter of the circuit, where you will work as a designer to develop it and to transform the numbers into real physical transistors that are providing the function that you want to achieve. And then, of course, after the design, you have the layout and the pre-silicon verification. And every step, you can always come back because something is not working. So for every step, there will be some milestone to achieve. And every step, you can fall back into the previous step if the milestone is not achieved. And of course, at the end of the chain, you have the post-silicon verification. This means you have the measurement. And after the measurement, eventually you have to rechange some requirement if the circuit is not able to achieve it completely. So about more going into the application. So which are the circuit that we will look now, and we are looking now, and that we will look in the next year. So we can, of course, span from power transistors, so single device with very high breakdown voltage, to very highly integrated circuit like microprocessor, very scaled with very low leakage microprocessor that are used to control, for example, displays, to control the CPU of the car. But in general, we can split the big car system into four parts. So we have the green mobility, which is everything related to how to make your car more green in the future. So it's going to the direction of electric car. Then we have the automated driving. So we are listening this topic since years, and we are getting closer and closer. And this is where I will also focus in the next slide. Then we have the connectivity. So for sure, to have automated driving, you need also to have a connection between cars. You need to send information. And this is where the wireless communication, like the 5G system that was presented before, and a Wi-Fi system, Bluetooth, will be considered in this field. And then, of course, you have also the security part. So in the present and in the future, we want to have easy access to the car, and then this need to be secure. And here we are talking about the ultra-wideband technology that also was presented during the day. So as you see, it's really a big bench of circuit, and we can span for many applications. And I will, in particular, focus on the autonomous driving. So to enable autonomous driving, you need to understand, the car need to understand what is around your car. So you need to understand the environment around the car at a certain distance. And then this car need to have a brain that react to this environment. So we have three particular sensors that can detect the environment outside the car. So you have the camera that was already presented also in the morning by our speakers. You have a lidar, which is a midway between radar and camera, and then you have the radar. And I will, in particular, focus on the radar because of the benefit of it. So the radar basically has the benefit that it's working also in extreme weather condition, while the camera is not. So if there is a very dense fog, the camera does not see through. And if you go to 100 kilometers per hour, you need to detect if there is a truck in front of you. And here the radar can help. And the radar was first time introduced in 2009 in a very high-end and luxury car, in particular in the Porsche Panamera. And our company, so Infineon, was developing the circuits for this radar. Then, of course, the car manufacturers saw that this was really beneficial, and they started to integrate it into different mid and low-end car going on with the years, till the moment as today where we have radar and camera working together and having different kind of sensor around the car and helping your car to understand what is around. And what we call today is highly automated driving, means that the car is suggesting you what to do, like lane control and speed control and tracking of the car which is in front of you. And the target for the next year is to have completely autonomous driving. And this means that this is another step of complexity. It's really a high step of complexity because you also need to deal with other safety requirements. So, in particular, how the car works, the radar for the car works. So we have a module which is we can be split into 3 parts. We have the real MMIC circuit, then we have a power supply module and the microprocessor. And high-level understanding, the module sent a signal. The signal reflects to a target, which can be car, truck, whatever, and then come back. And this signal is detected by the receiver and is converted by the analog to digital converter into a digital signal that can be processed. And you can represent these signals. These signals that are coming back to your receiver are different tones into your baseband. And I will explain this a bit better in the next slide. So, and how do you detect the speed of the other target? Simply, you send another signal in a time t equal n+1, and you reconstruct the same picture of your targets. And based on this, you can understand what is going on with your previous target. So you can see where the previous target is gone in the frequency. And since you know the time of flight and you know the speed of the signal, you can extrapolate the speed of your target. And you can understand if a truck is at the same speed, if it's going faster, slower, or if you have different target at the same speed. So this is all the core of the module. And then if you go more precisely into the theoretical and technical understanding of how this radar works, we can see that we need a PLL, so phase lock loop, that generate ramps, so ramps in frequency. And these ramps are sent by a power amplifier. Here we are talking about 76 to 81 gigahertz frequency. And the target reflect, and it's coming back into the low noise amplifier and into the mixer. So in particular, you see in the time domain, you are sending the ramp, and then the ramp come back a few moments later, after the time of flight. And this parameter tau is proportional to the distance, of course, of your target. And you can intuitively understand in this way that if you have a mixer, at the output of the mixer, in a certain time t, you have 2 different frequencies. And if you send 2 frequencies in a mixer, you will see the difference of those. So, and this is what before I showed you. This is the baseband signal. So this is what you have at the output of the mixer. You have the difference between the 2 frequencies. And this is proportional to the target. And then in the next wrap, you will see the same frequency moved. And from that, you understand the speed, the velocity. And here you can clearly understand the trade-offs. So if you have very fast ramp, this means that this time +1 and time +2, the time is really small, so you can detect very high speed. But to have fast ramps, you need a very wide bandwidth PLL. So this is the trade-off that the circuit designer has asked to deal with. And then this is the same representation. I just want to show you in a simplicity what are the circuits that are involved into the radar millimeter wave chip. Usually we have PLL, power amplifier, low noise amplifier, which is important to amplify the very weak targets and not amplify the noise, which is in the environment. Then we have a mixer that needs to be very linear. Then we have an amplifier that converts the output of the mixer to a level which is used by the analog to digital converter. we have itself the analog to digital converter, which is here very critical, and the critical performance is the dynamic range, because you need to detect far target, but also very close target. So in the very close target, it is very high, so you can have high voltage tones into your receiver and very small tone, and you need to detect the difference between them. And on top of it, the ADC need to have a very low distortion, otherwise you have ghost target. And then you have interfaces. And now going deeper and deeper into the circuit, so from high level understanding to deeper into the circuit, this is the most critical circuit for the radar, which is the ramp generator, so it's the phase locked loop, the PLL. So the PLL is working as a multiplier frequency, so you have usually a reference frequency which is very clean and very stable, and you need to create 80 gigahertz frequency. To do this, you have a local oscillator, which is LC, usually oscillator at this frequency, and then you have a frequency divider and a phase detector. And as I told you before, the performance here, the most important performance, is the speed of this ramp generator. Because to change the frequency to create ramps, you need to inject a tone into your divider. And if you calculate the transfer function of your PLL from the divider to the output, it is a low pass transfer function. And this means that you cannot create very fast ramp, so you are limited by the speed of your PLL. And from here, there is a big world that is opening on how to design this kind of PLL to achieve faster ramps. And this I can send you around a lot of reference, but it's really a huge world opening here. And now, to make you also understand, as Ali showed you in the morning, you need to know a little bit of noise, right? So what is the impact of the noise into this system? So clearly, if the system is without noise, you can see all the targets around. You can see the big truck, the small cars, and the small motorbike close to the truck. But in the case you have noise in the system, which in the PLL domain is called phase noise, this noise will be up-converted and down-converted by the mixer, and for every target you will have the shape of the noise around it. And if this noise is too high, it will cover the targets, the small targets. So this means that you have your truck and you have a car which is smaller, close to it, but you don't see the car in your system. And this is the most important problem in the radar. So you need to design PLL with very low noise to be able to see the close-by targets. And this is limiting the performance. And this is what it makes also the camera very attractive, because with the camera you can see much more. So those are all the trade-offs. So regarding the noise, how to control the noise of a PLL, usually you need to work in the local oscillator, the control oscillator, because at the border of the bandwidth of the PLL and above the bandwidth, this is the main contributor of the noise. And as you studied, maybe not all of you, but most of you studied the noise of local oscillator. You have basically the Leeson formula, which represent all the different parameters which you, as a designer, you can trick to improve the phase noise of an oscillator. Clearly, you have some parameter which is topology dependent. So, for example, the architecture that you select will influence the noise, and also some parameter which is technology dependent, like the quality factor. You are limited by the quality factor of your inductors and your capacitor. So you can clearly design a very good tank, but at a certain point you will be limited by the technology. And also you have another parameter which is very important, which is the flicker noise. This is the noise close to your carrier. And this is the noise which is hard to improve with the design. You can implement some architecture, yes, but at a certain point, this is still a physical effect that is present between the junction and the oxide of your transistor, and it's hard to get rid of it. So here an example of a typical LC oscillator with a PMOS and NMOS differential pair and the tank in the middle that create the RF frequency. So another important circuit is the power amplifier. So the power amplifier in the radar is really critical because it needs to achieve the right level of power to be able to transmit to 200 meter and the signal need to be reflected and still need to have a right level to be detected by your system. And to transmit such a high power like 15 dBm into the 80 gigahertz band with scale technology is not easy. So this means that here is where the designer like you need to push the limits of the technology to achieve the wideband, to achieve the right efficiency in order to do not burn all the system and to achieve the right power level. Here, as another example of a power amplifier with a cascade stage and the generation inductor and cross couple capacitors to improve the gain of the stage. This is typically used in a similar application. Now, so most of the talk is done because I wanted to focus on the radar, but still I want to underline that there are other modules that are very critical in the radar module, which is the microprocessor, the microcontroller, that take your digital data at high speed from the ADC. It processes the data, it does FFT, it implements some function, it understands what are the targets that are moving, what are the ghost targets, what are the targets that are not moving, and it provides the signals to other units like the control unit of the car, the wheel steering unit, the display unit. So, and this block is really critical because it needs to elaborate a lot of function. And then, not to under-evaluate the power supply module, which is also very important to create the right level of supply for your radar system, and which is typically from, let's say, from the battery to the core domain to different I/O domain, and all these domains need to be really well isolated. And on top of this, if the power supply module is having a poor isolation, you can see ghost target only because these performance are not enough. So you maybe create a very performance RF chip, but your performance are destroyed by the other module. So I want to underline that this need to be taken under consideration since the beginning to the system level analysis. And here a quick example of a power supply module that we develop with a block diagram. You can see, as I said, there are different output level, different regulators, different DC to DC converters, and this is for application like electric power steering and transmission actuators. And as I explained at the beginning, it needs to be compliant with functional and safety requirement and with high complicated temperature range, like up to 150 degrees. And as to stress again the fact that in the car we have really thousands of different circuits. This is just a slide to show you that based on the application that I presented you at the beginning, you can have sensing circuits, you can have connectivity circuits, Wi-Fi, Bluetooth, you can have complicated processor with memory system embedded, you can have on the other side only a few transistors with high power control level for like battery of the electric car control, and so high breakdown voltage devices. So there is really a wide spread of transistor and device which is involved into the car industry. So to conclude, I explain you briefly what is the process to create a circuit in a car. I explain you what are the circuits that are present today and what are the trends for the future, going to the direction of green mobility, autonomous driving, connectivity, and security. And I did a deep dive into the radar module with a PLL description, power amplifier, and a bit of microcontroller and power supply module understanding. So thanks a lot for your attention.